All right, day 5 of our work with limits. Let's talk about continuity of functions and how limits allow us to define continuity. But before we do that, let's use our calculator to find these limits. So if we're looking at this first one, the limit as x approaches 0 of 3 sine of 4x, and you can think of the 4x as inside that sine function, all over 2x. So our technique here is going to be to graph this function, or if you prefer, you can use a table, but I usually graph things. So go to your y equals screen and enter the function 3 times sine, and it gives you that parenthesis of 4x. Close the parenthesis, and then we are dividing that by 2x, which absolutely has to be in its own set of parentheses, just like that. If you do not put parentheses around the 2x, you will be graphing the incorrect function. Another note is when dealing with sine, cosine, or tangent functions, any trig functions, you need to make sure that your calculator is in the radian mode. So if you look at your calculator, it is this button right here. Hit the mode button, and then like the third option down will say either radian or degrees. Highlight radian and hit enter to make sure you are in radian mode. The only time you want to use degree mode is if you are doing problems that involve triangles and angles, specifically in degrees. Otherwise, you should be in radian mode. So recognize that we're looking at the limit as x approaches 0. So for your window on this function, you should choose some x values that are close to 0. I'm going to go -1 is less than or equal to x is less than or equal to +1. And I'm going to graph my y value from +10 to -10. You should end up with a function that looks something like that. If you do a bigger window, it's fine. You'll just end up with like some crazy thing like that. But it should still work for you. So remember our technique here. We can trick our calculators into finding the limits for us at specific points. So hit the trace button right here on your calculator. Hit that trace button, and then it'll pop up with an x equals, and you want to enter some value that is super, super close to 0, but not quite equal to 0. So let's go 0.00001, and it should tell you that the y value is 6, and so this limit is equal to 6. So now let's think about this second one. Limit as x approaches infinity of 400 over 2 plus 8e to the negative 0.3x. So again, you have to be very careful with how you enter this. You need to enter it as 400 divided by parentheses 2 plus 8 E, and to get to the E button, notice it is right there on your calculator, so you have to hit second and the division button. And then let's hit that caret button to raise it to the power of negative 0.3x, and then close that parenthesis there for the exponent. That's my caret button right there. If you have a TI-84, you don't need those parentheses, but it never hurts. So before we graph this, recognize that we are looking at an infinite limit. When we're talking about infinite limits here as x approaches positive or negative infinity, we are trying to find horizontal asymptotes. So we need to look at x values that are substantially large. And what do I mean by substantially large? Well, I just mean we need to look at some x values that are large enough so they cause our function to flatten out to some value. Now, we don't necessarily know what those x values that are large enough are going to be, so we should just try something. So let's go ahead and graph this function, and let's define our window to be, I don't know, -5,000 to +5,000. And once you've defined that for x, go ahead and hit zoom fit, option number 0, to get an adjusted y window. When we do that, we're going to get some really, really disgusting looking function that kind of looks like that. Now, it's going to look like poop on our calculator, but it's actually telling us enough information to find both of the next two limits. So if you hit the trace button, notice it kind of looks like a horizontal line up there. that is representing the horizontal asymptote that this function levels out to. So if you trace and move your x value over there somewhere, it's going to tell you that the y value is 200. Similarly, we could do the same thing over here in the negative world, and it's going to tell you some scientific notation with an e to the negative some big number like that. It's trying to tell you 0. So the limit as x approaches infinity is 200, and the limit as x approaches negative infinity is 0. And then finally, the limit as x approaches 0 for this function, well, it is continuous there, so it's just asking you to find the y-intercept. So type in an x value of 0, and you should get the y-intercept of 40. But if you think about these functions, you can identify these limits by thinking about the limit of this bit right here, 8e to the negative 0.3x. Think about what happens to that as x approaches infinity, and think about what happens to that as x approaches negative infinity, and you can figure out these limits without using your calculator. So let's move forward now and look at the two one-sided limits as x approaches 1 from the left and as x approaches 1 from the right. Notice now we have a piecewise defined function f of x. And again, this is just saying that to the left of the x value 1, the function behaves like x squared. So it's going to look like that. And to the right of that x value, the function is going to behave like the linear function 6x minus 5. So some linear function there. So let's find the left-handed limit. Well, notice first off that that is a polynomial function, x squared. So to find the limit from the left, I'm just looking at that x squared branch right there, and I can directly substitute in my x value of 1 because I don't have any discontinuities. So 1 squared is 1, so the left-handed limit is 1. We can do the same thing for that function right there, 6s minus 5, also a continuous polynomial. So when we substitute in that value, we get 6 times 1 minus 5 is also 1. So the left-handed limit is 1, the right-handed limit is 1, and notice that we have a greater than or equal to 1 right there. So f of 1 is also 1. That is our definition of continuity for a function. The left-handed limit equals the right-handed limit equals the value of the function at that x value. So now we're going to take that idea and apply it to a new type of problem. Notice again we have a piecewise defined function here, 3x squared plus 2 when x is less than 2, and kx minus 4 when x is greater than or equal to 2. So our goal here is to find that k value that makes this function continuous. So we have to use the idea of left-handed and right-handed limits. So we need the limit as x approaches 2 from the left of this function f of x to equal the limit as x approaches 2 from the right of f of x. And again, to the left and to the right, we're just talking to the left is less than 2, and to the right is more than 2. So we need 3x squared plus 2 to equal kx minus 4 when x is equal to 2. So let's substitute in 3 times 2 squared plus 2 equals k times 2 minus 4, just substituting in that x value there. And now we should simplify. 2 squared is 4 times 3 is 12 plus 2 is 14 equals 2k minus 4. Add 4 to both sides. 18 equals 2k. And so k equals 9. And now you should be able to plug that k value in to change that to a 9x minus 4. And we are saying that that makes this function continuous. And again, you could check it and make sure you are correct. 3 times 2 squared plus 2, does that in fact equal 9 times 2 minus 4? Well, 18 minus 4 is 14, and we already found that that side was 14. So yes, we are good. That k value checks out. Let's do one more problem here. Same exact idea. We need to find the value of k that makes this function continuous. Again, it's piecewise defined, so we are using that idea that we need the limit of f of x as x approaches 3 from the left to equal the limit of f of x as x approaches 3 from the right. So from the left, we are dealing with this branch up here, kx cubed minus 2x squared, and we want that equal, whoa, words, can't find them. We want that to equal the limit there, kx squared plus kx plus 12. So again, kx squared plus kx plus 12, and we are looking at the x value of 3. That's where we need to make this function continuous. So substitute in the 3. 3 cubed is 27k minus 2 times 3 squared is 9 times 2 is 18 equals k times x squared is 9, so we got 9k plus another k, and I missed my 3 there for that x. That should be x. Ooh, that looks bad. That should be xk right there, or kx, however you want to think about it, plus 12. And let's combine like terms and simplify. A 9k and a 3k, that's giving me a 12k right there. And that is the main idea of these problems. You are setting the branches equal to each other and solving for your unknown value. Now, you will see problems that are like this, but are piecewise functions with 3 different things defined. They are going to work exactly the same way, but you're going to have 2 different x values to look at. So sometimes you'll get problems with 2 unknown values, and you will need to use a system of equations to solve them. So go take a look at problems 11 through 14 on the study guide to check those problems out. And remember, there are videos for those problems already. So now let's change gears and talk about discontinuity of functions. So again, remember, it all comes down to factoring. Factor the numerator, factor the denominator. That is going to tell you a lot about your function. So we factor the denominator as a difference of squares, and we factor an x out of the numerator, and we see we have a whole at x equals 3. So again, a whole is a I'm a liar. A whole is a removable discontinuity. Whoa, I totally lost that word. Discontinuity. Discontinuity. A whole is a removable discontinuity, and we also have a vertical asymptote at x equals -3. And a vertical asymptote is a non-removable discontinuity. And again, think about how we find limits of functions like this. We can remove the whole and evaluate the limit for the modified function, but we cannot remove a vertical asymptote. I can't talk tonight. It is part of our function. It is non-removable, and there you have it. So let's talk about these 3 functions, which are continuous, which are discontinuous, and what type of discontinuities do they have. And for some reason, my minus signs disappeared, and I don't know why, but there they are. Now, notice that f of x is just a polynomial, and all polynomials are continuous. So number 1 is continuous. Number 2, notice we have a difference of squares in the numerator, which is going to factor as x minus 5, x plus 5, and so we're going to get a whole there, a removable discontinuity at x equals 5. And remember, a factor in the numerator will tell you your zeros, so that x plus 5 gives us a 0. It doesn't tell us anything else. But let's look at this last one. Again, that numerator is going to factor as x minus 4 times x plus 4. And again, x minus 4, x minus 4. So we have a removable discontinuity at x equals 4. We have a non-removable discontinuity on our DC at x equals -3.